Part 2 is on kinematics. This is the one where the physics people are like, oh, this is no problem, and those that didn't take physics are like, Okay. Stephen swims back and forth along a straight path in a 50-meter-long pool for 90 seconds. Stephen's velocity is modeled by that equation, where t is measured in seconds, and velocity is measured in meters per second. So we're like, right? This is the order of our derivatives. Derivative of displacement's velocity, derivative of velocity is acceleration. And so we want to find all the times in which Stephen changes directions and give reasons for your answer. So what's going to happen when you change this direction? His velocity is going to change from positive to negative. So we need to find when is that velocity equal to 0. And this is a calculator question, so you could just plug that into your calculator. Set your time from 0 to 90, and you would discover that at t equals 56 seconds, it's equal to 0. Some of you might also be like, ooh, I know that sine of pi is 0. So when t is 56, you could do mental math as well. Something about this mental math-wise, I'm just going to put a box around this to remind you that e to the anything has an asymptote at 0, right? It's never equal to 0. So the only part of this equation where something is equal to 0 could be with that sine part. Yes?
We still have to check like what the function looks like, because sometimes it might bounce back.
It might bounce back. If you look at this, are there any other x-intercepts? There's going to be one at 0, and there's going to be another one at 112, but it's only up to 9. So find Stephen's acceleration at time 60 and show the setup for your calculation. Indicate units. Is Stephen slowing up or speeding up or slowing down at time equals 60, and give a reason for your answer. So again, if we take the derivative of velocity, that'll give us our acceleration. Now this would be a place where if you type this into y1 already, just calculator stuff, I'm going to type it into y1, 2.38, just so we can see everything and we'll clear it out. Actually, get this up too. 2.38 e to the exponent. That's not e. E to the exponent of negative 0.02 x times by sine. Can anybody see what I could possibly run into a problem with what I'm doing right now? Kind of hard to see on my calculator, but maybe you can see it from where you're at. You see my calculators in degrees? And any kind of integral question that you're going to be doing with sine, cosine, tan, we need to make sure that our calculator is in radians. You'd hate to get a whole bunch of questions wrong just because you had your calculator set up wrong. Some of you are nodding because you have experienced this before. If I had set up my window to go from 0 to 90, this would have been the first part of the question. There's the graph. I might zoom out of this, but if I find this x-intercept, so second calculate my 0, number 2. Left bound looks good. And you know you can either click over like this, but if that takes you a really long time, you can just type in a number. And I know I'm going up to 80 to 90, so I'm pretty sure 80 will be to the right of that. And I push enter, and I get that 56 value. Okay? Now, I'm going to go out of here, because now we want to find the derivative. We want to find d dx, and here I can go and get y1. So a couple places where you can get y1 on your calculator, because if it says to, like go back to our question here, right? If it wants to find v prime of 60, I don't want to actually do that derivative by hand. If you have a calculator question, we're not trying, like that's a product rule and some chain rule involved. If you spend too much time on the calculator question doing non-calculator stuff, that's wasting your time. So I want to make sure that I'm going to go to my calculator, and I'm not going to rewrite that whole equation either. I already spent that time doing that in y1, so I want to put y1 into that. And you can find y1, I think it's alpha F4. Alpha menu is probably the quickest way to find that y1, and we're finding when x is 60. How fast was that? A lot faster than typing it all in again. Also a lot faster by doing the derivative and plugging it in. Don't want to go there either. So this is, right? And they'll only give you 1 mark for that. But where you're going to run into trouble is if you do things too long, you're going to run out of time to do other things on your exam. So just make sure that we're aware of how to do those things on our calculator. Give a reason, right? Is it speeding down or slowing up? So I also need, did I say that down? I said that last time too, speeding down or slowing up. Yeah, it's good times. I'm not usually at school this long. My brain power is all gone from there. V of 60, how do I find that from my calculator? Well, second, calculate number 1, a value. I can either do this for my graph and type in 60 and get the 0.159. That's option 1. You can also, on your calculator, I can go y1 and put brackets and make it like a function and get it that way as well. So those are both really nice ways to use your calculator to get those values. So going back, now I've got v prime at 60, v of 60, and how do we tell if it's speeding up or slowing down? The signs. What do we say if they're both negative? Speeding up. I like the idea of slowing up, speeding down. My brain is, I think it's also like a safety mechanism. I say crazy things all the time. So when eventually, if I get really old and my brain starts falling apart, people will be like, oh, he's just acting like normal. This is how he's always been. He's always said stuff that makes little or no sense. So find the distance between Stephen's position at t equals 20 and his position at t equals 80. This is not the distance he's traveled between those 2 times. It's just this time and this time. What is the distance between those 2? If we do the integral from 20 to 80, that will be an accumulation of change of what's happened when you started at 20 and then when you added or ended at 80. And it's just a displacement question because we want to know, right? It doesn't matter if I've gone back and forth here. If I started 1 tile away and now I've ended 3 tiles away, my distance between my start point and end point is 3. I may have traveled 30 to get there, but this question is just asking for a difference in displacement. And anytime we do an integral of a rate, it is an accumulation of change of whatever that integral is, in this case, displacement.
So why wouldn't it be absolute V of t?
Because absolute V of t, okay, so I'm going to model this here by moving, in the end, I'm going to start here, and I'm going to end 3 tiles away, okay? If I start here, go 6 tiles, and then come back 3 tiles, I've traveled 9 tiles. But what is the question asking? What is the distance between my position at time 20, which was here, and my position at time 80, which ended up here? What's the distance between those 2 positions? Not how far did I travel to get there. So this, I find this question is kind of, it uses the word distance, but it's asking you a displacement question.
That's just messing me up.
That's definitely going to mess somebody up, right? And then part D, this is where we're getting to what's the total distance that Steven swims over the time interval from 0 to 90. And this is where we add those absolute value bars. And since it's calculator, I would do it right inside the function, right? Important that you don't do it on the outside of the function. Has to be on the inside of that function. All right. So we see a couple of things that could be problematic with kinematics. In the example before, that maximum speed, you have to think about speed being the absolute value of velocity, so you have to be careful. If you've got a huge negative velocity, it might actually be your biggest speed. This one, sometimes it's easy to forget the speeding up and slowing down. The signs are the same, you're going to be increasing in speed. If one's positive, one's negative, then you're going to be decreasing in speed. Okay. Example 2. 2 particles move along the x-axis. From 0 to 8, the position is given for particle P by this function xp of t. And particle Q by, they give you the velocity of particle Q by vq of t. Particle Q is at position x equals 5 at time 0. Okay. From 0 to 8, when is particle P moving to the left? If it's moving to the left, we know its velocity is negative. So here's the derivative of x. Okay, it's going to be a chain rule. This question, did it have a calculator beside it? No, that's why we're doing it this way. So the derivative will be the velocity function of this particle. And it's easy to see from this equation that the only place it's equal to 0 is where your numerator of a fraction is equal to 0, so t would have to be 1. If we do our diagram for our function here, between 0 and 1, it's going to be negative. From 1 to 8, when we plug in values, it's going to be positive. You might even want to, can you factor the bottom? No, not really, eh? No. Thought it would factor this, but it does not. So based on that, it's moving to the left between the times 0 and 1. Can you see why you could include 0 but not include 1? Like at 0, if I plug in 0 into my equation, you see you get negative 2/10. So at 0, it's already moving left. It already has a negative there. But at 1, that's where it's equal to 0. That would be when it's stationary, or changing directions from moving left to moving right. Or possibly just changing, well, yeah, we go from negative to positive. Between 0 and 8, find all the times which the two particles are traveling in the same direction. So we got our velocity for Q, and we can figure out when it's equal to 0 at t equals 3 and t equals 5. And I'm a little bit mad at my diagrams here because I like it when the 8s match up. If you imagine a perfect vertical line like this, they do match up just wonderfully. And there's this parallel vertical line right there at 3. How about we just redraw them? Okay? I'm going to take away those blue lines. I'm going to erase the answer for this just temporarily. And I'm going to start at 0, go to 8. Here's 0. Here's 8. And I'm going to mark on this one. Here's 1 to scale. This would be 3 to scale. 5. And we know this one is negative in that section. This one is positive in that whole section, but I put 2 plus signs just so that we could see them. We know that everything is positive on the top one from 1 to 8, so all of these sections would be positive. We know it's negative between 3 and 5, and then positive. If you draw things this way, does it not become a lot easier to see that they're both positive here, and they're both positive here? What are those sections? From 1 to 3, and 5 to 8. So taking the time to draw things to scale as much as possible, but above each other. I can see it from here too, but it takes a little bit more thinking. By drawing those dotted lines right above it, and labeling the sections more than once, right? This whole section was positive, but I can write positive all the way through. And it's really easy to see where both of them are the same. Find the acceleration of particle Q at the time t equals 2. Is the speed increasing, decreasing, or neither? Explain your reasoning. So, our acceleration will be our derivative, and our derivative is easy to find here, just 2t minus 8. And at t equals 2, easy to plug in, that is negative 4. We also can plug in 2 into the velocity equation, and we get 3. One of them is positive, one of them is negative. So we know that the speed is decreasing because they have opposite signs. And then last part here, find the position of particle Q the first time it changes direction. So it's going to change direction when its velocity is 0. We already figured out its velocity was 0 at 3 and 5, but the first time would be 3. Its position at 3 would be its starting position plus an accumulation of change of everything from 0 to 3. And that accumulation of change would be the integral of the rate. So the integral of the velocity equation of Q from 0 to 3 plus the 5 that we started with. This equation here, just a question, how many people have made the connection that when we write this as accumulation of change, really this is, you know how the fundamental theorem of calculus part 2 says this? F of b minus f of a, okay? Can you see that when you're trying to find the second part, f of b, we could just take this f of a and put it out in front? That's all this is. This is f of 0. This is our position where we started. And we're just adding the change, the integral. So we're just taking the second fundamental theorem of calculus part 2 and just sort of like rearranging it and using it as a new thought process. And in our new thought process, we're saying our position at a new time point will be where you were in the past. Where did you start? And how much have you changed? And that'll be our final answer. So integral of this is not hard. Plugging things in. And we get our position. Instead of ending the video, what I'll do is I'll go and just, there's question 3. So if you're later on, if you like decided, hey, I'd like to do these at home or I wanted to try them, you can pause the video at this point, see the answers for 3, for 4. You have to zoom in probably online, and 5. But I've got the whole page showing up. So all the answers are there. Yeah, and then we'll start